All right, well, welcome to a beautiful snowy Thursday up here in Tahoe. Um, we're wrapping up week 4, if you can believe it. We're a third of the way done with this class, which means things are coming up, right? We've got the project that's due next week and also exam 1 next week. And my plan today is to pick up where we left off. I want to show you another discrete probability density function. You may recall that last I showed you 2. I showed you the binomial, which was the when there are just 2 answers to the question, yes or no, or whatever variation you want to call it. And we saw a little bit about how that worked. And then I showed you what's called the geometric distribution, which is you keep repeating an experiment until you get a success. Like what I did was the tossing of the coin until I got heads. So we talked about that one. The one I want to show you to kind of wrap up the discrete probability density functions is one that's called the Poisson distribution. And after that, we'll start looking at continuous probability density functions. And we'll see how they behave a little bit differently, the similarities, but the differences in them. And the goal today, hopefully I show you 2, the continuous, one that's called uniform. We'll for sure get to uniform. Uniform distribution is just when everything is just as likely. And then the other one I'm going to show you is what's called an exponential distribution function. And we'll talk about that one. So that's the plan on my end. But as always, I like to open it up to you guys at the start. Are there any questions on anything that we've been doing so far? Any questions on the homework or topics that we've talked about that you're confused on?
I think it's binomial functions that make no sense to me.
Okay.
But I don't know, we were going through it and it was just jumbled in my brain. I don't understand binomial functions.
Okay, so maybe I'll give you just sort of a quick recap on the idea of the binomial probability density functions.
Okay, that's fine. Thank you.
I can definitely do that. Anything else that people want to talk about? Seeing there are no homeworks due tonight, of course, nobody's been working on them. Hopefully you've been working on your projects, and that's where most of your effort is. Okay, so let's talk a little bit about binomial probability distribution functions, just to kind of refresh your memory and how they work and all that. I'm going to go ahead and turn on my whiteboard so I can write some stuff as we're going. So let me go ahead and share that here real quick. All right, so when we have binomial probability density functions, first of all, the way that we designate them, erase that green, is this. So we've got our variable, and it's coming from a binomial. So we use the capital B to show that it's a binomial distribution. And then for binomial distributions, we need to know 2 things. All right. One is we need to know n, which is going to be the number of trials. Okay, so when I say trials, it could be toss of a coin is a trial, roll of a die is a trial, asking somebody the question is a trial, and so on. So this is the number of objects, people, things, events that are going on. Okay, so we need to know the number of trials, and then we also need P, which is the probability one too many eyes on that, probability of a success. All right, so we can define success however we want. Okay, this is going to be this is the probability that a quote unquote successful event occurs. And so in the binomial distribution notation, we're going to write those two things. So we're going to write B with an N comma P. So an example would be, let's say we've got X is coming from B of 12 comma 0.3. So the way to interpret this, what this means, the 12 is that there are 12 trials. So 12 events, 12 people were asking, 12, maybe we're looking at, dogs, 12 dogs that we're looking at specific qualities or whatever. So that's what this is. And then the 0.3, this is the probability of success. Okay, so having a successful trial, whatever successful could be. So, for example, let me just put some words onto this. This could be something where we are going to randomly pick 12 bears in the Tahoe Basin. Right, and we know that there's a 30% chance that they are under 2 years old. Okay, so now this I'm completely making up. I have no idea if that's even accurate, that there's a 30% chance if you take some random bear out there in the woods that they are under 2 years old, but I'm going to say that. All right. So this would be the kind of thing that leads to a binomial distribution, because when we go out there and we look at a bear, only two things can happen. They are either under 2 years old or they are not under 2 years old. Right? So it all comes down to the question that we're asking that makes it binomial, because if what we were doing was just going and finding these bears and figuring out how old they were, that's not going to be binomial anymore, right? Like if it's how old is this bear? How old's that bear? How old's that bear? That question's not a yes or no, right? We're going to get different values depending upon the age of those individual bears. But this one's a, is this bear under 2 years old? 30% chance of yes and a 70% chance of no. Okay, so this is when we use binomials, when there are only two possible options. So then what we're going to be interested in, once we know what our distribution is, we're probably going to be interested in probabilities, right? Probabilities of specific things happening. So let's go with in the context of this. What if we wanted to know, what is the probability that 4 of the bears are under 2 years old? All right, so maybe that's a question that we were curious about. It's like, all right, well, what's the likelihood that 4 of them are going to be under 2 years old? Okay, now, because it's a distribution, we know a lot of those distributions have, these distributions all have formulas for calculating probabilities, but most of them will have these formulas programmed into something. So like if you've got a handheld calculator, that'll be in there. Most online resources will have them as well. And for this one, we're going to use Binomial Pdf. All right, so Binomial Pdf, and anything PDF, because you'll see for all the distributions, there's a geometric PDF, there's a uniform PDF, there's an exponential PDF, there's a normal PDF, there's like all of them have this. The PDF part, what this tells you, this is the probability of one value occurring. all right, or the probability of one, maybe not value. Let's do result. I like that word better, so I'll change that. So since I'm only looking at one result, I want 4 of these bear to be under 2 years old. That's going to be a binomial PDF. We would still use a binomial PDF if we wanted to figure out what's the probability that 6 of them are under 2 years old, or what's the probability that 1 of them is under 12 years old, or none of them, or what have you, right? So this is binomial PDF. Now I'm going to go ahead and calculate this. Obviously, depending upon what type of technology you have, you're going to get to it in a different way. If you haven't figured that out yet, that's going to be homework over the weekend. Make sure you figure out how to calculate PDFs and CDFs for these distributions. All right, so like mine, I've got a stats window, and under the stats window, I have a menu, and there are lots of different things I can do there. One of them says stats or tests, another one says calc, and then there's one that says distr for distributions. And when I look under that distribution command window in that menu, I've got all kinds of stuff. I've got normal PDF, normal CDF, TPDF, TCDF, chi-square PDF, chi-square CDF, FPDF, FCDF, right? Poisson PDF, Poisson CDF, geometric PDF, geometric CDF, and I also have binomial PDF and binomial CDF. So like I said, there's lots of these. And I know you keep hearing all these letters. Just remember PDF, short for probability density function. That's your probability of one specific value, right? Or one specific result. Okay, so I'm going to go to mine. And what mine asks for, and yours is going to be similar, it first asks for the number of trials, right? And then mine's even nice, and it tells you that's n. So for this one, I'm going to put in 12, right? I'm going to put in 12 for n. The next thing it asks for is probability of success. It says prob success, but probability of success, and it even says letter P. All right, so this is where I'm going to put in 0.3, because that's the probability that a bear is under 2 years old. And that's what I'm considering a success. All right, and then it asks me for X value, capital X value, and capital X, again, if you come back and you look at this real quick, remember the capital X, that's our variable. That's the thing that we're looking at. And so this is the 4. I want to know what's the probability that I get 4 from this group of 12. Exactly 4. So I'm going to put 4 in for that. All right, so it asked me for those 3 numbers. So I put in 12, 0.3, and 4. Okay, so I hit enter and I let my calculator do its thing because it's super awesome like that. All right, so let me just put here. So we did PDF. Let me change the color back to black. So we did PDF. So we did 12, comma, 0.3, comma, 4. So this is the notation I'm going to use whenever we write these out. I'm going to write it as NP and then X, because that's what my calculator asked for. That's what most technology is going to ask for in that order. So I'm going to do it that way. All right, so I run the numbers on that, and it tells me it's 0.231114. We'll stop it there. Okay, so this tells me what's the likelihood that when I go and I grab 12 bear and look at them, what's the likelihood that 4 of them, that exactly 4 of them are going to be under 2 years old if there's a 30% chance that any one of them is under 2 years old. So think of this as a percent. I regularly just immediately convert these to percents. by moving the decimal 2 spots. So there's a 23.1% chance that that's going to happen. 1 in 4, basically, right? 1 in 4 chance would be 25%, so it's pretty close. So basically, if I were to go and collect a group of 12 bear, and then do another group of 12, another group of 12, another group of 12, another group of 12, about 1 out of every 4 of those groups is going to have exactly 4 bears that are 2 years old or younger. Okay, so that's kind of the idea with this question. So let's do another one here real quick that's related to this. Let me just change color so you recognize it's a different question. How about this? What's the probability that how about at least 6 of them are under 2 years old? Okay, so this time we're not going to use PDF because PDF gets us one specific value. If we did the PDF, the binomial PDF with 6, that would be telling us what's the probability of getting exactly 6. But I don't want just 6. I want 7 and 8 and 9 and 10 and 11 and 12. So one option would be to do all those different PDFs. What's the probability of getting 6? Add that to the probability of getting 7, plus the probability of getting 8, plus 9, plus 10, plus 11, plus 12, and so on. Okay, but that's too much work. So instead, we have a command that's called Cdf. Okay, so for this one, we're going to use binomial Cdf. And the C stands for cumulative. So this is what we use when we want to get an interval of values. Okay, so instead of just one value, we want to accumulate them. We want to add them up. We want to make the cumulative where we have a certain region. Okay, so now what your CDF is going to do really depends on your technology. What I showed you last time when I talked about CDF, and this is probably a little bit of a product of my age. The CDF I was taught is from 0 up to and including the number that you're interested in. Okay, so like if you were to do CDF of 6, that would be 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6. It would add up all those probabilities. My technology, so I'm going to guess if you've got another version of the TI, it probably is similar. It still starts by asking the same thing. It starts with, what are a number of trials? How many trials are you going to do? And what's the probability of success? So that's still this 12 and 0.3. But now mine actually says lower value and upper value. So I can actually take care of this one by doing lower value of 6 and upper value of 12. So for mine, and I think I'm going to go with this as kind of our notation for binomial CDS as well. We're going to start with N and P, just like before. But then we're going to put 2 more numbers, and those 2 numbers, these are going to be the lower bound, and this is going to be the upper. Okay, so you can probably see why I used 6 as my lower bound. At least I hope you do. right? Because I want to know what's the probability that at least 6 of them are. So I don't want 5, I don't want 4, I want at least 6. So I'm going to start with 6 of them. Why is my upper bound 12?
Because you chose 12 bears.
Yeah, because that's the total, that's the number of bear that I'm actually picking up and looking at, right? So I can't have more than 12. It is possible that all of them are under 2 years old. Probably not likely, right? But it is possible that all 12 of them are, so that's why I want that as my upper bound. All right, well, let me run the numbers on this and let's see what we get. Okay, so the number I got for this is 0.1178. And as a percent, that's around 11. If we round it, it's around 11.8%. So that's not very likely. That's about 1 in 9, just so you know. All right, that's about a 1 in 9 chance that going to be at least half of them are under 2 years old. Okay, so it's possible, but it's not quite, it's definitely not as likely as getting exactly 4, right? It's half as likely as getting exactly 4. All right, so Allie, you just said you got an error saying quote unquote argument. Okay, okay, here's the deal, guys. I don't know what kind of technology you're using. All right, so maybe you can tell me what kind of calculator are you using? All right, TI-83. All right, TI-83 plus, and then an 84 for Willie. Okay, so my advice with those, because I don't have one, so I can't really look at it and play with it, but I do know that the book walks through the commands for the TI-83s and 84s and both the regular and the plus. Let me see if we can maybe find it real quick here. Give me a second. I got the book pulled up. I'm just going to scan it real quick, see if I can find it back in this chapter. But I do know that it definitely walks you through that. I think if you use the online version, if you don't actually download it, but you just use the online version, I believe that it even has, like when you run into the ones, you can like click on the little calculator icon and it will kind of walk you through it. Don't quote me on that because, again, since I don't have one of those, I don't do that. Let's see. I think I'm getting kind of close here. Oh, okay, that was geometric. I just shot past it. Hold on 1 second. Okay, so I just found something that's going to help us there. It's on page 256. All right, so 256. And it shows what to do. So actually, let me share my screen. I'll show it to you guys. All right, so hopefully everybody can see this. So when you're reading the book, look for this little icon. Look for the little computer icon, and then it'll say here, using the TI-83, 83 plus, 84, 84 plus. Right? So to calculate x equals a value, you use Binomial Pdf, put in parentheses n comma p comma your number. Okay. So that's just like what we talked about. Now for this one, it says the binomial CDF, it's going to give you for x less than or equal to a value. So it is actually doing what I learned, which is the from 0 on up. So you're still going to do n comma p comma a number, and that's probably why you got where it said argument or whatever, is because you were giving it an extra number. So let's talk about how we're going to be able to calculate this one using that specific command. So let me go back to the whiteboard and we'll talk about that. All right, so let me go ahead and clear this stuff off. Or no, I don't want to clear it all off. I want those things still there. Let me erase. And I'm going to erase over here. So give me a second here. I got too many windows open. I got to move something around. All right, so let me just erase this real quick. So if you're using a TI-83 or a TI-84 or one of their plus versions, it's really important to realize that when they do, or when that one does a binomial CDF, again, it's n comma p comma, let me call it x, no, I'm going to call it A. Okay, this is the probability that x is less than or equal to A. So if we were to do binomial CDF of this one with the 12, 0.3, and then 6, okay, this is the probability that x is less than or equal to 6, which is not what we want, because this would be saying, this would give us the probability that there are fewer, or there's 6 or fewer 2-year-old bears, right? So, and that's not what we want. We want greater than. So we're going to have to get a little bit sneaky here. All right, now this is definitely, I mentioned this at the end of last time, but let me draw a picture. I think sometimes if you see the picture, it makes a little bit more sense what we're doing here. So think of this as just the real number line, where we got 12 and we got 0. Because those are the extremes of what we could get, right? We could actually sample 12 bear and have none of them be under 2 years old, or we could sample and find all 12 of them are. So those are our different possibilities. Now, what we're looking for are the ones that are, that at least 6 of them are older. So we're looking for, now somewhere on here is 6, that's about halfway. But let me mark the values that we're, whose probabilities we're interested in. We're interested in 6, 7, 8, 9, 10, 11, 12. I'm going to have to make my line just a little bit longer to make that my 12. Okay, so we're looking for values of 6, 7, 8, 9, 10, 11, or 12. Okay, now what that really means is I want to exclude a bunch. I want to exclude 0, 1, 2, 3, 4, and 5. Right? Those are the ones that I want to remove. Well, these 5, I can actually get their probability by doing the binomial CDF of 12, 0.3, 5, right? That's going to add up less than or equal to 5, because that's what the TI-83 and 4s do. So if I were to calculate that binomial CDF, I have the probability of 0 through 5. Well, I don't want the probabilities of 0 through 5. I want the rest of them. So how do you get the probability of the rest of them if you know the probability of the 1 through 5 or 0 through 5? How about this? What if I told you that these two sets are complements? Remember, complement is the other things. What do we know about the probabilities of complements? So I'm going to take it nobody remembers. So
What was the
complement.
question?
How are the probabilities of complements related?
Sorry.
It's okay. All right, they add up to 1 because remember what a probability of 1 means? Probability of 1 means it's going to happen. So think about this specific example. If I were to look at the probability of getting 0 young bears, the probability of getting 1 young bear, 2 young bears, 3 young bears, all the way up to 12 young bears, if I were to add all those probabilities up, I'm going to get 1. Because for sure, I'm going to get one of those results. So what we can do, if we want to exclude some results, we can get that this probability is going to be 1 minus the binomial CDF of 12, 0.3, 5. So that's what you're going to need to do when you're using a TI-83 or 84. I guess mine, because I have a TI-89, it's a little bit later developed. It does a little bit more, I guess. It allows me to actually put those lower and upper bounds. But you guys can still get those values. You just have to think about it in a different way. So in general, if you want a greater than or equal, you can subtract off the binomial CDF of the smaller number, of the number 1 under where we're looking. Right now, I notice that in the chat box, Willie said he did 1 minus CDF plus PDF. And let me make sure that I understand exactly what you mean with that. Let me just erase over here. And I'm going to put some numbers in there, Willie. So I'm going to say, so you did 1 minus CDF of 12, 0.36, and then added PDF of 12, 0.36.
Yeah, exactly.
Okay. That's what I thought you meant. I just wanted to make sure. And yes, that's actually going to get you the value as well. And let's look at what happened. So let's start with the 1 minus CDF of 6. Okay, so CDF of 6 is going to give us the sum of all of those. All right, so that's this guy right here, the CDF of 6. That's going to give us the probabilities of 0 plus the probability of 1 plus the probability of 2, all the way up to plus the probability of 6. So when we do 1 minus that, we're getting the remaining group. But notice that that remaining group, so that's the 1 minus CDF. That one's not quite right for what we want, right? Because we want at least 6 of them. We need 6 as well. So we need to get that one put back in. Well, this one gets put back in by that guy right there. So that's why that process works with the 6s on there. And I think I mentioned last time that this is the better way to think about it, because when we get to continuous, there is no one smaller. Like with discrete, since it's countable, we know the next thing smaller than 6. it's 5. But if it was continuous, if you can have decimals and fractions and whatnot, what's the next number smaller than 6? I mean, there isn't a next number smaller, right? Because I could go 5.99999 with a million nines. And I can still actually get closer to 6, put some more 9s on the end of it. So for continuous, it's better to think about it this way. But we'll cross that bridge when we get there. All right, so just realize that when you do the binomial PDF, you're getting the probability of one specific value. And when you do binomial CDF, again, depending upon which technology you're using, it's giving you an interval, right? It's giving you an interval of values. And it appears that the TI 83 and 84 gives you from 0 up to and including whatever number you tell it. All right, so at this point, I don't even remember. Was that Ashton that asked me about this? I think.
Yeah, it was me.
Are you feeling any better about it? Does it make a little more sense?
Yeah, it does. It's just the calculations that really confuse me.
Okay. Are you feeling better on that?
Yeah, like the setup and the difference between the PDF and the CDF make a lot of sense.
Okay.
But yeah.
Okay, cool. Well, that's what I want to hear. I mean, obviously, it's going to take some practicing and running the numbers. Along those lines, let me give you another big recommendation. And I think a lot of students don't do this, but this can be really, really helpful. In the book, let me go back and share the book again, just so I can kind of show you what I mean. And since the book is free, right, you've got free access to it, there's no reason not to go in here and do this. But what's really nice about this book is it actually will walk you through problems. Let's find, okay, so like, let's look at this guy real quick. So 2013, Jerry's Art-O-Rama Art Supplies Catalog, blah, 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 right? So it says there are 560 pages, 8 feature signature artists. So suppose we randomly sample 100 pages, right? Let X be the number of pages that feature signature artists. So it will kind of walk you through, including calculations, right? So like the first one says, what values does X take on? Well, if we're sampling, right? If we've got the 8 pages with signature artists, all right, so we can have 0, 1, 2, 3, 4, 5, 6, 7, or 8 of them. All right, so what's the probability distribution? It's binomial. We're sampling 100 pages, and then we need the probability of success. And the probability of success here is getting a page with a signature artist. Now, they don't have it as a decimal, but they've got it as a fraction, 8 over 560. Where'd that fraction come from? Let me go up a little bit so you can see the bit about it again.
It was the sample outcome over the total outcome.
Yeah. Think about the total number of possible outcomes. That's the total number of pages in the catalog, which is 560. How many of them have signature artists? 8. So that's 8 out of 560. Okay, so you could get a decimal for it. I don't know, and this is legit, I don't know about a TI-84. I know my TI-89, I can put 8 over 560 in it. That's fine. You might have to put a decimal in. You might not. You can play around. But that's kind of my point with this one, is that it will walk you through and say, okay, here's the next question. What's the probability that 2 pages feature signature artists? Well, we're going to do a PDF because we want exactly 2 pages. So we're going to do a PDF, 100 comma 8 over 560, because that's our N and our P. And then it's going to be comma 2 because we want 2 pages. Spits out a number. So you can check and see if that value is what you got. when you did it with your technology, and you can see if you're doing it right, if you're doing it properly. So I'm a huge fan of doing that, especially when you're trying to figure out technology at the beginning, especially, right? I'm going to guess that most of you have never tried to do any kind of a probability density function thing on your calculator in your life. And that's okay, right? You've never had a reason to, but because it's new to you, you're not comfortable, you're not certain, right? There's a lot of question on whether you're doing it right. Use this to help you till you start doing it enough that you start going, oh, okay, this is the process. Here's what I put in, and I get my values. So I highly recommend going to the book because they will walk you through. They'll even show you things like, look at this one, the part 3. It was, what's the probability that more than 3 pages feature signature artists? So we're looking at the probability of X greater than 3. It even shows you to do the 1 minus, because we're going to use our complement, right? So you're going to use your complement. So 1 minus this one, it's a CDF because we're adding up all the values up to including 3. So that's why I put the 3 there. And there's our magical number, right? So use the book. Don't rely just on what I talk about in class. I mean, hopefully I'm a good resource and hopefully I'm giving you good information, but use the book too, because the book has tons of examples, right? Like there's another one about pancreatic cancer, right? So in every section, you're going to see 2, 3, 4 different ones. And even better, I don't know if you guys have noticed this. Let me scroll down a bit. I want to get to the end of the chapter, right? So at the end of the chapter, they have things like experiments that you can do. So you can work on putting in the numbers and practicing things, right? So here's another one, lucky dice experiment. I don't assign these, but they're there as things that you can do to practice so that when it comes time for quizzes and exams, you feel you're a little bit stronger on them. Anyway, all right, so I think maybe that's all I want to talk about as a review for binomial, because I think, Ashton, you said you're feeling better about this. But before I jump up to the whiteboard and start doing new things, anything else from before we want to chat about? All right, well, hearing and seeing none, I'm going to hop up to the whiteboard, so I'll be right back with you. All right. Oh. Sorry about the earthquake, guys. Give me 1 second here to set this stuff back up again.
Are you injured?
What's that?
Are you injured?
Am I injured? No, I made it to the doorway in time.
Okay, good.
But real quick, here's your Star Wars t-shirt of the day. You may go, that looks kind of familiar. This is another Starry Night inspired one. I told you Starry Night is my favorite painting, so there you go. And just so you know, because I'm sure some of you are like, is he buying shirts just so he can do it? Nah, these are all shirts that are actually in my closet, so I'm that big of a Star Wars nerd. All right. Anyway, so remember what we're doing here with these distribution functions. Binomial that we spent some time on just a little bit ago. It's basically giving us probabilities for all the different events. So kind of think about when we would make, say, a frequency table, right? Where we'd go, these are the number of times that these different things can happen. We're basically generating the same kind of thing, except we're making it a relative frequency, right? Probabilities are long-term relative frequency. So in essence, we're making a frequency table. Think about that example we just did when we were talking about the bears, right? And we were catching a set of 12. You can imagine that what we've got is a chart that has the number of bear and the probability, right? So this is the number of bear that were under 2 years old, let's say. So we have 0, 1, 2, 3, 4, 5, 6, right? And this would go on down to 12. And every time we calculate one of those PDFs, we're getting the value in that probability. So I don't remember which one it was. I think it was maybe the probability for 5. That was like 24 point something. Yeah, I'm just going to go with it. But we got like, so this was 0.243 or something like that. Well, we could do, what's the probability of 4? And maybe we get 0.316. And the probability of 12 is very small, you know, or whatever. So we're basically filling in this frequency table. Okay, so that's what the probability density function is doing. It's giving us the probabilities, it's giving us the relative frequencies for the different results. So I'm just trying to tie this back to what we've already seen because it feels like it's completely different, right? I mean, it's called something different. We have to use our technology now to calculate it. So it feels like it's a completely different thing, but it's not. We're just using the technology to get these numbers for us quickly, but it really means the same thing, right? And what we do know is that if you add all those probabilities up, you get 1. And that's kind of the key thing for probability density function. Each one of these probabilities is between 0 and 1, but when you add them all up, you get exactly 1. All right. So last time I showed you binomial, 2 possible outcomes, right? The bear is either under 2 years old or it's not. You either have brown eyes or you don't. The head comes up heads or it doesn't, right? Those are all things that are binomial. And then I showed you geometric, and geometric was, it's kind of like the binomial, where there are 2 options, but you keep going until you have success. And so what that was measuring is how long do you have to go until you are successful, right? And so those probabilities, there's a probability of needing that many times for it to happen. So we looked at tossing a die, but it could be anything. It could be or tossing. I said that last time too. Tossing a coin, or we could roll a die, right? And maybe it's we want to know how long we have to roll until we get a 6. Well, that would be a geometric probability density function. We would put in our probability of success, which would be 1/6. And then if we wanted to find out, well, how often do we need to go 10 times? You would put 10 into that geometric probability density function, and it would tell you what's the probability of needing 10 rolls to get a 6. Okay, so that's what the geometric did. Now, the third one I want to show you, that's discrete, and there are a bunch of discrete probabilities, but I'm just going to show you these 3. But the third one is what we call the Poisson. I got to make sure I spelled that right. No, yeah, Poisson distribution. So it's not poison, unless you're like from Indiana, then it would be poison. No offense if you're from Indiana. My family's all from Indiana, and Indiana, they have cities like there's a city in Indiana, just on the side, spelled this way. How would you pronounce that?
Brazil?
Okay, yeah, so would I call that Brazil? Now, if you're in Indiana, It's Brazil.
Nice.
It's Brazil, Indiana. How about this? How would you pronounce that one?
Peru.
Yep, I call it Peru too, but if you're in Indiana, it's Peru. It's Peru, Indiana.
What the
Another
heck?
one. There's another one that's spelled Versailles, the palace in France, but it's called Versailles. Right, so that's what I'll say. If you're in Indiana, this is Poisson. This here is the Poisson distribution. But it's actually called the Poisson because it's French.
Nice.
I digress. I love the Hoosiers. Don't get me wrong. I definitely love the Hoosiers, but they got a funny way of speaking sometimes. All right. So the Poisson distribution, like the others, is discrete, right? So we're looking at when this is going to occur. But this one's a little bit different. We use the Poisson distribution when we're interested in how many events are going to occur in a given interval. All right, so this could be something like we're curious to know how many people are going to walk into the grocery store in 30 minutes. How many airplanes are going to land at the airport in this hour, or something like that. The interval doesn't have to be a time interval. It can also be like a length. It could be how many trees do we expect to find in this next 100 meters, right? Or anything like that. So this is when we use the Poisson distribution. Now, what you need to know for the Poisson distribution, because like for all of them, remember we had to have some sort of a metric, something that we measured. For the Poisson distribution, what you need to know is actually how many events are in a specific interval. Okay, so what we're going to see with the Poisson distribution is it's going to be written like this, the symbols. We use P for it, Poisson. And you're going to have mu. All right, and what mu is the average number of events in your given interval. All right, so let's say we're talking about people coming into a grocery store, and we know on average, there should be 5 people per 10 minutes. If our interval was 10 minutes long, mu would be 5. If our interval was 1 minute long, we'd figure out what that 5 people per 10 minutes reduces down to. If it was an hour long, we'd figure out how many people that should be per hour and so on. So whatever time period or whatever length or whatever we're dealing with, we need to know what's the average number of events we should see in that time period or in that length or in that whatever interval. All right, so let me give you an example. Let's actually look at one of these so you can kind of see how they work. And what if I told you this? So on average, the moon is struck by 3 meteors every hour. I have no idea if this is true or not. I'm just making this up. All right, but let's just say that. We know on average, the moon gets hit by meteors 3 times every hour. Okay, so this is going to be a Poisson distribution because we have a certain number of events per time period. All right, so here's my first question. What's the probability of getting 2 strikes in a half an hour? So I know how many should happen, right? I know in general that there are 3 meteors every hour. But what's the likelihood that if I just look for half an hour, if I watch the moon for half an hour, what's the likelihood that I see 2 meteors hit it? Okay, so let's talk about what we're going to have to do to calculate this. So my first question to you is this going to be a PDF or a CDF? What do you guys think? PDF or CDF? All right, I'm getting a couple of PDFs, just got a CDF. So I guess that means we get to start fighting over it. So this one's going to be a PDF. And it's a PDF because we're looking for exactly 2 strikes. Remember, when it's an exact number, that's when we use the PDF. We use the CDF when it's a interval of numbers. Okay. So this one's definitely going to be a PDF. All right, so in your calculator or in your technology, there should be something that's called a Poisson PDF. All right, now, again, I don't know exactly what you're going to have to put into a TI-84, but I do know that there should be 2 things that you put in. All right, one of them is the mu. Okay, now for the mu, in this case, this has to be the expected number in 1/2 of an hour. I need my interval for my mu to match the interval that I'm curious about. So since I was looking for how many, looking for 2 strikes in half an hour, I need to know about how many should I get in half an hour. Okay, so how many should I expect in half an hour? Good, 1.5. Right? If I expect 3 in an hour, I should get 1.5 in half an hour. Okay, so I'm going to put in here 1.5 for my mu. But then I have to tell it how many I'm interested in. So I'm looking for 2. I'm looking for 2 strikes in this half an hour period. All right, so I just used my calculator to calculate this, and I got a probability of 0.251 blah, 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 or 25.1%. So what this is saying is that if the moon is struck by 3 meteors every hour, you go and you watch for half an hour, there's a 1 in 4 chance that you see exactly 2 meteor strikes. Okay, so Poisson takes care of this kind of question. Well, just like with the PDF, there are CDFs for the Poisson. So let's ask another question here. How about this? What is the probability that the moon is hit by no more than 50 meteors in a day? So we're just going to watch for the entire day. All right, so we start the clock right now. And we're just going to keep watching for meteor strikes until 24 hours later. Right? And I want to see what's the probability that we don't see more than 50. All right, so this is looking for then the probability that x is less than or equal to 50. Right? I don't want more than 50, but 50 is okay. I can have exactly 50, and that's going to be fun. So this is looking for what's the probability that x is no greater or is less than or equal to 50. All right, so PDF or CDF? Which one do we need here? Good. Getting some CDFs thrown at me real fast. This one's going to be a CDF because we're looking for all the way up to 50, 0 through 50. Okay, so this is going to be a Poisson CDF. So again, let's think about what we need to put in. So we need a mu. Mu needs to be the average number of meteor strikes we expect in our time period. Well, our time period is a day. So on average, how many meteor strikes should we get in one day? All right, so I see 72, I see 150. Well, here's how I'm going to figure that out. On average, I have 3 meteors every hour. There are 24 hours in the day. So what I should expect my mu to be is 3 times 24, which is what Willie put in as 72. So on a day, in a day, we should expect around 72 meteors because there are 3 every hour. So our mu is going to be 72. And then the maximum number we want is 50. All right, so before I calculate this, questions on how I got that mu? Because I bet there are. You guys see how that happened? All right, I'm going to trust that you guys are okay with that. Okay, so I'm going to go to 72, and I want to know how many, or what's the probability of getting up to and including 50. And what I got for my probability, 0.00393 blah, blah, blah. which is 0.4%. Not 4%, 0.4%. Okay, this is a very small likelihood. That's 4 out of every 1,000. 2 out of every 500, 1 out of every 250. So the way to interpret this number is that we're going to see 50 or fewer meteor strikes only once out of every 250 days. That's like 8 months. So if the moon is getting hit on average by 3 meteors every hour, it's highly unlikely that there's going to be a day where it's hit by 50 or fewer. It's very unlikely. Okay, so that's how you interpret these numbers. But notice that this is still a discrete probability function. There's a countable number of meteors that are going to hit. It just behaves differently because it's a different kind of question, right? It's not binomial. We're not saying, did it get hit by a meteor or not? We want to know how many of them. And it's also not geometric where well, let's just keep going until we get hit by a meteor. No, that's not what we're looking at. So it's answering a different question. And that's what we're going to see with probability density functions in general, is we get different PDFs, we have different functions to relate to different scenarios, because not all scenarios are the same. But all probability density functions are the same in the fact that, like in the case of all these discrete ones, the sum of all the probabilities is 1. And we're really just counting up, we're making this long-term relative frequency. Right? That's what probability is. All right, so there's your third discrete probability density function we're going to talk about. Like I said, there are others. There's another one that's called like hypergeometric. And I mean, there are bunches. But I wanted to show you these three because they all kind of make sense in terms of what they're doing. And they're all kind of important. And they're all a little bit different. Okay. All right, well, let's take a break. My clock says 4:42. So let's come back at, I'm going to shoot for 10 minutes, 4:52. And we'll start looking at the continuous probability density functions. And we'll see how they're similar, but how they're different. And I'll start introducing you to, well, we'll at least see one. Hopefully we'll get to both of them today. All right. So you will know I'm back when you see the screen pop back up. All right, but I'll see you guys in 10 minutes, all right, at 4:52. All right, so now that we've seen discrete probability density functions, let's turn our attention to continuous probability density functions. Now, they have the same idea, right? They're the exact same kind of idea, except now we don't have countable results. Remember the difference between discrete and continuous. Discrete, we can count the results, right? We can count the meteor strikes. We can count the bears that are under 2 years old. We can count how many times it takes to get ahead on the tossing of a coin. Those are all things that we can count. Continuous are going to be for the things that we can't count, right? That can take on decimal values and fractional values and all that. So maybe we're going to be looking at the heights of children. Maybe we're going to be looking at the times, the amount of time it takes for papers to get graded or whatever, right? As soon as it becomes something that we can't count, we're going to need different distribution functions. So these are the ones that are continuous. All right. So same idea as before, except now we're not building a table. And we can't even really think about the probability of any one specific result. All right. So here are some things that are a little bit different now that we're looking at continuous probabilities. First of all, the probability of an exact value is actually 0. So let's say we're looking at the distribution of heights of full-grown adults. Now, if we were to look at all the adults in the world, we have all kinds of different heights. And even if someone says, you know, like I'll say I'm 6 foot tall, or I'm 6'1", I'm neither. I'm actually kind of between 6 and 6'1", depending upon the day and what time of day and all that. So if we wanted to get really precise, I'm 6 feet and, you know, I don't know, 0.684 inches or something like that, right? So it's not a countable number, and there are going to be other people that are similar height to me, a little bit taller, a little bit shorter. There are going to be some people that are very much taller, very much shorter, but there's this huge variety in heights of people. Right? Okay, well, if you were to look at a probability density function and say, what's the probability of finding someone that's got exactly the height 6 feet tall? That probability is actually 0 in a continuous distribution function. Right? Because all of you out there that think you're 6 feet tall, you're probably not exactly 6 feet tall. You're probably not exactly 6 feet 0 inches. You're going to be close, but you're going to be off by just a little bit. And so that's why the probability is actually 0. So this is a little bit different, a little bit weird, right? That when we do continuous probability density functions now, the probability of one exact value is 0. So instead, what we do is we calculate probabilities of intervals. So if we get back to that example of 6 feet tall, so now maybe instead of saying, what's the probability of finding someone who's 6 feet tall, I'm going to say, what's the probability of finding somebody that's between 5.99 feet tall and 6.01 feet tall? I specify an interval, and now I can calculate the probability. So I'm going to put a star next to this one because this is a big change. This is a big difference. Before, with the discrete, we did calculate literally what's the probability of this specific number. We don't do that anymore. There are a few exceptions, but in general, no, we don't do that anymore. We find probabilities of intervals. Okay, so how do you do that? Well, what we do is we graph the probability density function, and the probability is the area below the graph of the PDF. So here's the other big difference. When we go to a continuous probability density function, we're going to draw a picture. There's actually a function like you remember maybe from math classes before, the old plug in x, get out of y. But there's going to be a function that describes the probabilities. And we're going to look at the area underneath that curve. That'll give us our probability. let me draw a picture for you. Let me show you kind of what I mean. So hopefully you remember how to graph functions. But here is a function, let's say, and let's say that it gives us a function that does something like this. All right. Now, the graph of this, what this means, the horizontal is our x. That is our variable. And I mean variable in terms of statistics, right? It's the thing that we're counting. So it's the number of meteor strikes per hour. It's the height of a person. It's the whatever. Okay. So that's got, that axis has the variable. The other axis has our probability. So first things first, when you look at a graph of a PDF, when it's up higher, those are values that are much more likely to occur. When your graph goes lower, those are things that are less likely to occur. All right, so like on this graph, I can tell you right now that these are likely results. Because they're higher, right? There's a hill there. That hill means those things are much more likely to occur. I also know that these guys out here are unlikely. Because those probabilities are low. They're near zero, right? Remember, probability of zero, that would be down here on this line. So if we're close to this line, they are unlikely. The further we get away from that axis, the more likely they are to occur. Okay, so this is how you can kind of read a PDF if you're given a graph, just in terms of things that are likely, more likely, less likely, and so on. Okay, but now, like I said, the probability is the area below the graph. So let's say that we were going to be looking between two numbers. Those two numbers, I'm going to use letters, because of course I am. This is math, right? Let's say we're looking at A and B. Okay, so we're looking at the probability that X is between A and B. That's actually going to be the area under this graph between A and B. So I'll go ahead and just kind of patch this in here. But that orange on the graph, whatever value that area has, that would be the probability that X is between A and B. Okay, so that's what I mean when I say it's the area below the graph. And that's a difficult question to answer, right? I mean, if I were to ask you right now, what is that area? Even if I gave you numbers on here, you'd probably go, I have no idea, right? Like, think about it. What shapes do you know how to find areas for? You should be able to find the area of a rectangle, right? Like that's what. Circle, pi r squared. Triangle, 1/2 base times height, right? So we've got some shapes that we know areas for, but something like that, no clue. Well, you can actually learn how to do that, but it requires calculus. And I know I probably just scared some of you off, but in calculus, one of the things that we learn is how to calculate areas under curves. So I think I may have mentioned to you guys that I took a probability and stats class as a math major. Maybe I did, maybe I didn't. But it wasn't until my senior year, and it was super math intensive. And that was one of the things we did, right? We used the calculus to actually figure out probabilities of a lot of these things. You're not gonna have to do that because you got the technology, right? That's why you have the TIs. That's why we've got the computers, so that they can actually calculate that stuff for us. All right, but that's what's going on with these things, and that's very different because we never once talked about the graph of a binomial distribution. We didn't talk about the, I mean, just today, right? When I showed you the Poisson distribution, I didn't talk about the graph of it because there is no graph. I mean, like, you could make one, but that's not relevant because they're discrete. We only have to worry about the graphs when they're continuous. Well, this also then tells us if the probability is the area below the graph, then we know that the total area is going to equal 1. So if you were to look at the total area underneath the graph, it's going to add up to 1. Because that's what's necessary for density functions, right? Probability density functions need the sum of all possibilities to be 1. Well, in this case, the sum of all possibilities is the total area equals 1. All right, so that would mean if I were to just look at the total area here, so let's make it kind of this reddish brown. All of that area equals 1. All right, so that's kind of similarities and differences between discrete and continuous. So let me introduce you to your first continuous probability density function. This is a nice one. Hopefully you like this one because it's actually really nice. It's called the uniform probability density function. All right, so if you think about the word uniform, I know that it has multiple meanings. One is, you know, an outfit that you wear that describes who you are, right? Like a soldier's uniform or something like that. That's not what we're talking about here. This is the adjective, the descriptor. Things that are uniform are regular. They're just always the same, right? And that's what a uniform PDF is. This is all outcomes are equally likely. So that means that no one result is more likely than the other. Now, you can have uniform discrete probability density functions, and that would be like the rolling of the die. Right? Think about rolling a die. As long as it's a fair die, not loaded or anything, you're just as likely to roll a 1, a 2, 3, 4, 5, or 6. So that would be uniform. In the context of what we're doing, we're going to say we're going for something that's uniform but continuous. So here would be an example. Let's say you're at the beach. So you're taking a vacation or you're out at the lake. I wouldn't go hang out at the beach today. It'd probably be a little bit cold. But suppose you're out on the beach and you fall asleep because it's a beautiful day. And then you wake up and you start looking at the water and you start your stopwatch, maybe your mental stopwatch, and you go, okay, I'm going to time how long it takes until a wave crashes on the beach. It's going to be just as likely that that wave crashes 1 second after you open your eyes as 2 seconds, as 3 seconds, right? There isn't going to be a time period that's more likely than another. All right. So something like that would be a uniform probability density function that's continuous. Because it's not like we can count. It's going to be exactly 1 second or 2 seconds. It could be 0.763 seconds, right? So that's why it's going to be continuous. All right, so all outcomes are equally likely. So let's think about what the graph of one of these things is going to look like. So again, if this is our amount, so maybe the amount of time we got to wait till the beach crashes or the wave crashes on the beach. This is our probability. What is that graph going to have to look like? Can you describe it?
Would it be straight?
Yeah, it absolutely would be straight. Because remember, it means it says all outcomes are equally likely. So let's pick a probability. Let's say this is our probability for any one given time. Okay, so there's that probability, there's that probability. They're all going to have that same probability. And so if I do that for every one of these x's, what I get is a horizontal line. Absolutely. So I think that was you, Carrie. Good job on that one. All right, so it's just going to be a horizontal line, and then it is going to stop somewhere. It is going to stop somewhere because, like, think about that, the wave crashing on the beach. It's not like you're going to have to wait an infinite amount of time for a wave to crash on the beach, right? Eventually, you're going to see one happen. So it's going to end up stopping somewhere. But this is what a uniform probability density function looks like. Super easy. This graph is just a horizontal one. All right, well, remember this, that the total area below the graph equals 1 in one of these things. Well, this is a rectangle. And hopefully you remember that the area of a rectangle is the base times the height. So we know that the base times height is going to have to equal 1. All right, so the base, let's just say that we're going from, say, A to B, just some 2 different values. The length of the base is going to be B minus A, just the difference in those 2 values. Now, in this example of the waves crashing on the beach, the smallest value is 0, because it's not like that wave is going to crash negative time. And there is the possibility that as soon as you open your eyes, you see a wave crash, right? So it is possible to go from 0 to whatever. But there are other distributions where you go, well, no, the only possible results are 4 through 10. All right, well, if you want to know the length of the base, you just subtract those 2 values. Okay, and then the height, well, that's just the probability. So with uniform distributions, you can actually calculate what the probability is going to be. The probability is going to be 1 over B minus A. So that's kind of nice, actually. When you have a uniform distribution, you get the probabilities quickly. All right, now, that doesn't mean that you're going to get uniforms a lot, right? Uniforms are kind of rare. But when they do happen, they're super, super nice in terms of finding their probability. All right, so let's go to that wave example, and let's do some numbers here so that we can actually calculate some probabilities. All right, so let's say that a wave crashes on the beach every 10 seconds. So it's just nice and regular. So this, of course, is a mythical beach, right? It doesn't exist in real life, but well, it's our thought experiment. But all right, so we see the wave crash. 10 seconds later, another one comes. 10 seconds later, another one comes, and so on. Now, it's not that big of a stretch, honestly. I don't think I've told you this, but my background, I'm also a scientist. I'm not just a mathematician, I'm a scientist. And what I did with my first grad work was I actually looked at how tides move sediment. It's not exciting. I didn't swim with dolphins or anything like that, but I looked at how tides move mud and sand. So it's actually fairly realistic that waves happen regularly, depending upon really the shapes of stuff, but it's not that big of a stretch. So let's just say that it's going to happen every 10 seconds. So that means if we were to open our eyes, we might see something happen, see the wave crash right away at 0. We might have to wait until 10 seconds, right? Because maybe the wave crashed right before we opened our eyes. It could come anytime in between. And so if we are going to start drawing a graph of this probability density function, we're going to go from 0 out to 10. So those are our A and our B. So what's the probability here then? What is that value for our probability in this case? Good, Willie. It's 1 over 10. Right? Plug in those numbers, 10 minus 0, 1/10. So on our vertical axis here, we're at 1/10. So here's our probability density function. And it's boring, horizontal line, but it looks like that. Okay, now, the reason I wanted to draw this is so that we can actually calculate some probabilities. So how about this? What's the probability that the amount of time that we have to wait until we see a wave crash is between 2 and 5? All right, so there's our interval. Like I said, with continuous distribution functions, we have to have an interval now. So we're looking at what's the interval. Well, the interval is 2 to 5. So you open your eyes, and what's the probability that you're going to have to wait some length of time between 2 seconds and 5 seconds to see this wave crash on the beach? Okay, we're going to calculate this geometrically. We can calculate areas easy here. They're just rectangles. All right, so here's what I'm going to do. Let's mark 2 and 5 on our graph. So 5 is the halfway point, and then 2 is, I don't know, probably right around there. So we want to know what is the area under this graph between 2 and 5. So I need to know the area of that rectangle. All right, well, since it's a rectangle, it's base times height for the area. The base, actually, let me write it. So it's base times height. The base is going to be 5 minus 2. That's that length, also known as 3. The height was that probability that we just calculated, 1/10. So we get 5 minus 2 times 1/10 is 3/10. So the probability that you have to wait sometime between 2 and 5 seconds to see that wave crash is 3/10, 0.3. So it really is as easy to calculate probabilities. Given an interval, you just mark your interval. And in fact, if you want to know the probability, let's generalize this. So the probability that X is between, let's not call them A and B. Let's call them capital A and capital B. Well, that's going to be B minus A times your probability. So we already know how to calculate the probability. Now we just have to multiply it by the length of the interval. So you could also use this for, like, what's the probability that we have to wait more than 7 seconds? Okay, well, you would mark that more than 7, so 7 to 10. Figure out its length, multiply by the 1/10, and you're good to go. So basic probabilities are pretty quick here. Let me show you conditional. Because conditional are also not terrible if you think about it geometrically. All right, so here's another probability I want to do. Let's look at what's the probability that x is going to be greater than 4 given that x is less than 9. So hopefully you remember this notation. The vertical bar tells you that it's conditional. And what conditional probabilities do is they restrict the possibilities. Instead of having all possible outcomes, we're restricted. So like now, we're restricted to less than 9 seconds. So we're not looking at the entire length here. We're looking at less than 9 seconds. And then if we're less than 9 seconds, what's the probability that we have to wait more than 4? So I'm going to recycle this picture. I'm going to erase the 2 and the 5 because we don't care about those guys. But now let's put on the 9 and the 4. So 9 is somewhere over there, and 4 is probably right around here. Now I'm going to color code this. I'm going to show you 2 different things with my color coding. The first one, I'm going to show you the restriction. All right, we're restricting ourselves to x being less than 9. So instead of having the entirety of the rectangle, of the original rectangle, I'm only going to have that bit that's to the left of 9. So I'm going to do this with these sort of blue dashes. Okay, but there's our restriction. All right, now let's look at the interval that we're curious about. And the interval we're curious about is x greater than 4. So I'm going to do that in orange. So x greater than 4, we start at 4, and we need to be bigger than it. But notice that I'm stopping at 9. I'm not going beyond 9 because I need to be within that blue rectangle. This was the condition, right? I have to be less than 9. All right, so there's a picture of what's going on. And if I want to calculate this probability, basically what I need to know is what portion of the blue is shaded orange. And there are a couple of ways to do this. Okay, so let me show you the 2 ways we can do it. The first is just think about the lengths of those intervals. The blue goes from 0 to 9. That's length 9. So I have 9 total length possibilities for outcomes. The portion that I'm interested in, the part that's orange shaded, goes from 4 to 9. So that's length 5. So this probability is actually 5 out of 9. So if I already know that I don't have to wait more than 9 seconds, the probability that I have to wait more than 4 is 5/9. So I like to do it this way because it's pretty fast. This only works for uniform, though. It only works for uniform because everything is just as likely. All you have to worry about is the lengths of the intervals. Okay, so let me show you this other way that's more robust, meaning if you have a different kind of density function, not uniform, you can still kind of do it the same way. So the other way to think about this, because this was like interval lengths, is to think of it as the areas. I'm going to put here area of interest divided by the restricted area. So I'm using the same color coding scheme here just so you can see. So the orange area of interest was the 4 to 9, and the restricted area was the 0 to 9. It was what we had after our initial restriction. All right, well, watch what happens if we do that. So the area of interest, it's got an interval of 5 times a height of 10. So it's 5 times 1/10, which is 5/10 on top, which is, let's reduce it down to 1/2. So again, all I did was I did base times height. The height is 1/10. We already calculated that. The base was 5 from 4 to 9. So 5 times 1/10 is 5/10, which reduces to 1/2. All right, so let's look at the restricted area. The restricted area is interval length 9 times a height of 10, which is 9/10. And of course, that doesn't simplify down. But what we've got is 1/2 divided by 9/10. So hopefully you guys all remember how to deal with fraction division. You just flip it over and multiply. So this becomes 1/2 times 10/9. And if you simplify that down, you get the exact same 5/9. All right, so you can probably see why I like to just think of it as interval lengths, because it's way faster. But again, I can't reinforce this enough. That only works if it's uniform distribution. If it's not uniform distribution, you have to do it with the areas. The area of that you're interested in divided by the area that got restricted. Okay, so just realize that this is how you have to do it every time it's not uniform, but uniform there is a fast way. All right, so how are we feeling about uniform distribution? Is it making sense? Give me a thumbs up if we're feeling okay about it. Yeah, all right, seeing lots of thumbs up, awesome. All right, so the next one I want to show you is what we call an exponential probability density function. All right, so this is an exponential distribution. You know what, I think I forgot to tell you, I forgot to show you with the uniform, is the symbols we use to show that it's uniform distribution. It's actually really easy. And it's going to surprise absolutely none of you. It's U, but then we put in here the two values A and B, where that show the interval of allowed amounts. So like in that example that we just did with the wave crashing on the beach, it would have been uniform 0, 10. Okay, so it's super easy, but I don't want that to throw you if you see that in a homework problem and go, whoa, what the hell is that? No, the U is just telling you uniform, and then the two numbers are telling you what the bounds are on the possibilities. Okay. Anyway, I digress, but I had to catch that because I was just about to show you what the exponential looks like. All right, now what this one is, it's kind of similar to what we were talking about in the waves example of waiting for something to happen. All right, but we use this in general, when we're figuring out the amount of time until something occurs. All right, so with the waves crashing on the beach, if it wasn't a regular event, if there was some randomness to it, then we would have to use exponential distribution. Okay, and I want to make that perfectly clear. Right, so there's the amount of time until something occurs, but it's not regular. Because if it's something that happens regularly, then it's uniform. Okay, so there's a little bit more randomness to an exponential distribution. All right. Now, what you need when you do an exponential distribution is you need to know the average time it takes for this thing to occur. So we're going to go ahead and call this mu again. All right. So mu is the average time something occurs. So let me change the wave crashing on the beach thing to make it exponential. So when we did it uniform, I said a wave crashes on the beach every 10 seconds. Okay, so on clockwork, every 10 seconds. Exponential distribution would be waves crash on the shore on average every 10 seconds. Do you see the difference? I can't set my watch to the waves here. For the uniform, I can. They're going to happen regularly, every 10 seconds. There's another wave comes crashing down on the beach, right? So for exponential, it's a wave comes crashing down on the beach on average every 10 seconds, right? So it's just like, it doesn't happen regularly, but we know roughly when it happens. So hopefully you're kind of seeing the difference. All right, this is not regular, but we do know on average. Okay, so mu is going to be the average time that something occurs. So what we need to do when we've got an exponential distribution, if you've got the mu, you need to calculate m. And m, it's going to equal 1 over mu. So it's just a reciprocal. We use the letter m because it's the English equivalent of the Greek letter mu. But this guy m, if you want to think about it this way, this would be the rate at which this thing is happening. So if waves crash on the beach on average every 10 seconds, there's 1/10 of a wave per second, basically, right? It's doing that same kind of thing of trying to get a number of waves per time period, kind of like we saw with earlier thing. Now, the reason that we calculate this m is because that m is what we use when we describe the exponential distribution. So we're going to have x. This one we write exp for exponential. And then we put the m, so not the mu, but the m. All right, so that's the notation you're going to see for an exponential distribution. All right, now, nice thing about exponential distributions is we've got a good formula for the PDF. All right, so for exponentials, the PDF equals, it's f of x equals m times e to the minus mx. Now, if you ask me where that comes from, I'm going to tell you, well, that's just how exponential distributions work. If you really want to know where it comes from, again, you need some calculus. The calculus will definitely show you why this function, well, okay, it's exponential. That's what this e to the power is. Hopefully you remember e. It may have been a while, but e is a number, just like pi or anything else. It starts, it's 2.71828, blah, 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 blah. It never repeats, goes on forever, just like pi. But it's called the natural base. You may remember natural logarithms, and I know horrible flashbacks just happened. Well, that's where this e, that's what that e is, but it's exponential. But depending upon what that m is, which was 1 over mu, you can get a slightly different form. All right. Okay, well, since that's our PDF, we can actually draw a graph of this. This is what it looks like. So again, here's our x, here's our probability. And what this looks like if we draw the graph of it, it's going to start up here and then decrease exponentially towards this axis. So if you remember the term asymptote, line that we approach, this is a horizontal asymptote for this graph. We get really, really close to 0. We never quite get there, but the further you go out, the closer you get to 0. This value right here, this probability, this is m. If you put 0 in here for x, e to the 0 is 1. So you end up with just m. All right, so remember how to interpret these graphs. What values are most likely in here? What values of x lead to the most likely occurrences for an exponential distribution? All right, so remember what's most likely are the ones that are higher up. So these are the most likely results. Really, really small values of x. Less likely are the big values. Okay, so that's why this works really, really well if we're going to talk about the amount of time that we're waiting for something to happen. Right. So let's go back to that waves crashing on the beach every 10 seconds. We probably are not going to have to wait minutes for the next wave. We're not going to be way down here. We're most likely going to see it in the first few seconds because it's most likely to happen every 10 seconds. Right. So that's why we end up getting shapes like this, and that's why it applies to these kinds of things. All right, so there's your PDF. So again, if we want to know probabilities, just like before, we said, okay, well, what's the probability that it happens in this interval of time? We're looking at the area under this curve. All right, well, same thing for CDFs. Remember CDFs, those are cumulative starting at 0. So if I wanted to do a CDF, let's choose a value here. Let's say that this is A. This area right there would be the CDF of A. All right, well, if you run the math on it, if you do the calculus on it. I'm not going to do it to you. I'm just going to give it to you. But if you were to actually do the calculus, what you end up seeing for the Cdf formula, if we're looking for the probability that x is less than or equal to a, so I'm calling it a, this probability is 1 minus e to the minus ma. So it's nice. We just have a formula. You just have to plug it in. You might not actually have this on your calculator. I know mine doesn't have the exponential distribution on it. But I think that's because the calculation is really, really easy to do. You don't have to really do much. You just have to know that m, but that m is given, right? We've got that if we know on average how often it occurred. And then the a is also going to be given because we want to know, well, what's the probability that we don't have to wait any more than this amount of time. All right, so let me do an example. Let's actually run some numbers on one so you can see how this plays out, and then we'll call it a day. So let's keep talking about waves crashing on the beach. But we're going to change this just a little bit, right? Before I said they happen every 10 seconds. Now, let's say, we'll change the number as well, but let's say a wave crashes on the beach on average every 5 seconds. And here's what I want to calculate. We're going to calculate two things. One, what's the probability that we have to wait between 3 and 6 seconds to see a wave. And the other one we're going to ask is, what's the probability that we have to wait less than 2 seconds? Okay, so two different questions. So the one's going to be, what's the probability we have to wait between 3 and 6 seconds? And the other is, what's the probability that we have to wait less than 2 seconds? Let's actually start with the second one, just because we've got the formula here and we're ready to go. Right, so we're looking for what's the probability that we have to wait less than 2 seconds. So this is the probability that x is less than 2. The one above it, this is the probability that x is between 3 and 6, right? So that's just the notation that we use for probability. But let's look at number 2, because number 2 is a CDF. You want to know how long we have to wait less than 2 seconds? I just plug it right into here. But I have to figure out m. So let's figure out m before we get going, because we need m. All right, so how do you get m? Do you remember?
It's 1 over mu, right?
Okay, good. It's 1 over mu. And I see Willie just threw it in the chat box, and so did Carolina there. It's 1/5. Okay, so m is equal to 1/5. So mu is the, on average, how long it takes for this thing to happen. So that's the 5 seconds here. All right, so let's use this formula to calculate the p of x less than 2. That's going to be 1 minus e to the negative 1/5 times 2. So that's 1 minus e to the minus 2/5. All right, well, we definitely need a calculator for this one. So let me crack out my trusty sidekick here. So 1 minus e to the minus 2/5. And I get 0.32968, which as a percent is 32.97%, or roughly 33%. So we're going to put there right here is around 33%. So there's a 1 in 3 chance that we're going to have to wait less than 2 seconds. All right, now before I step off of this, I don't know if anybody caught this and is a little concerned. When I first wrote the CDF, I wrote it as x was less than or equal to a, right? Because that's what CDF means, up to and including. For this one, I was saying we wanted to wait less than 2 seconds, which was less than, not less than or equal. So if you didn't catch that, I'm mentioning it now. Is that a problem? Did I just use a formula I'm not allowed to use? Well, the answer to that question is no, it's totally fine. Because the difference between less than and less than or equal is the equal part, right? So the only difference between what I just calculated here and the CDF would be the probability of exactly 2 seconds. But what's the probability of exactly 2 seconds? What's the probability of exactly any one specific event on a continuous distribution? Yeah, it's 0. So less than or equal, same. That also applies to like the uniform distribution when we did the, between A and B. It can be less than, greater than or equal, less or equal. It doesn't really matter. The or equal has no effect. All right, well, anyway, so there you go. There's the probability that we have to wait less than 2 seconds. So let's answer part 1. What's the probability that we have to wait somewhere between 3 and 6 seconds to see the wave crash? So let me draw the picture again. And we'll just sort of visualize this a little bit. So it's exponential, which means it's decreasing. So it's up here and coming on down. All right, this was 1/5. Remember, m was 1 over mu, so 1/5. And we're looking between 3 and 6 seconds. So here's, say, 3, and here's 6. So we're looking at wanting this area right there. Okay. Well, I would say if we knew calculus, this would be easy. Unfortunately, I think the only person in this group that knows how to do this with calculus is me. And there might be a couple others, but since we don't know calculus, do we have enough to do this? Spoiler alert, we do. We do have enough to do this. We just have to get creative. Because we really only have one formula, right? We've got a formula for less than or equal. We don't have one for somewhere in between or more than or anything like that, right? We've got just less than or equal. Well, check this out. Let's think about the CDFs for 3 and 6. And I'm going to color code them again. So let's do the CDF for 3 in this sort of brownish red. And let's do the CDF of 6 in purple. So CDF of 6 is going to give me this purple area, right? It's the area from 0 up to 6. It's the probability of getting anything up to and including 6. The CDF of 3 is going to give me the area from 0 to 3. So I'll do that in this, again, kind of reddish brown. So look at that geometrically. Do you see how we can get the orange from those two? Like, let's just talk it in colors. What operation am I going to do with the colors purple and red? Can anybody see it? If I take the purple area, there you go, Willie, subtract the red, that's going to leave me my orange, right? So from this, we're going to get that orange is equal to purple minus red. So I need to do CDF of 6 minus CDF of 3. All right, well, let's put these in here. For the 6, that's going to be 1 minus e to the minus 6m. We'll put m in a second. And then the other one's going to be 1 minus e to the minus 3m. So I'm just putting 3 and 6 in here for A. But now I'm going to do a little bit of algebra. I've got 1 minus 1. Those cancel each other out. I'm subtracting a negative. Makes that a plus. So I get e to the minus 3m minus e to the minus 6m. And let's put in our m now. It was 1/5. So we get e to the minus 3/5 minus e to the minus 6/5. And now I'll grab my calculator. So let's see. So we get e to the minus 0.6 minus e to the negative 1.2. And what I got was 24.76. So 0.2476, which is around 24.76%. So it's right around 25%. So 1/4 of the time, we're going to have to wait between 3 and 6 seconds for that next wave to crash. All right, so not nearly as nice as doing calculations for uniform, but we've got formulas for it. So it's actually really quick and easy to do. So real quick, before we call it a day, I just want to show you one more thing. I left it in this form with the M's, just so you can kind of see what's going on, and we can generalize it. So in general, for exponential, we want the probability between two values, A and B. It's going to be E to the minus MA minus E to the minus MB. And that's what we saw here. A was 3, B was 6. And so this might be worth putting a box around. Because this way you don't have to do the algebra again. We already did the algebra once, we'll call it good. All right, so there's the exponential. So we've now seen two continuous distribution functions, uniform and exponential. And next time I'm going to introduce you to a third. This is the biggie. This is the biggie. It's called the normal distribution. And we're going to use the normal distribution a lot. So we're going to spend a lot of time on it because going forward, it's the one that's most important. Okay, so a couple of things. So first of all, Tuesday, next class, that is when your project number 1 is due. Right? It's not due in class. You just have to submit it by midnight. All right, I only need one copy of it. As long as I've got all the names of the people that are in that group. Right? Remember, you're in groups of 2 or 3. As long as the names are on the paper, you don't all have to submit it. All right, so you can just submit one for the group, but make sure that somebody submits it by midnight through Canvas. I definitely need it as a PDF file. All right, if you did it in Word, you can save Word as a PDF. Right? It's actually really easy. This one, I need it as a PDF file, no photos. PDF. Right. So that is due on Tuesday. Our first exam is a week from tonight. I know on the syllabus it says chapters 1 through 6. It's only going to be chapters 1 through 5. We're a little bit behind schedule. I will send a notification out with Canvas to remind everybody on that as well. But it's only going to be chapters 1 through 5, which is up to and including what we did just tonight. This stuff is chapter 5. Okay, so that's going to be on Thursday. Don't forget also that their next homework sets are due Tuesday night at midnight. I also changed that so that chapter 6 stuff is not on there. I delayed that a week as well. I adjusted everything since we're a little bit behind. Okay, but make sure you get in, work on the homeworks by Tuesday night at midnight, get into your project by Tuesday night at midnight, and start prepping for that exam that's going to be on Thursday, chapters 1 through 5. So busy time right now. I know it's a really busy time, but well, we're at that point in the quarter. All right, so with that, let me wish you all a wonderful weekend. Get out there and enjoy the snow. If you're a skier or a boarder, get up on the hill there once the winds kick down, and have yourself a good old time. All right. So have an
Thank you,
awesome
Bruce.
weekend, and I'll see everybody on Tuesday.